Good afternoon, good morning, good evening, everyone. Welcome to session 7 of our EVPN series, where we're going to discuss EVPN gateways, specifically EVPN gateways for hierarchical EVPN for scaling and DCI. Mitch, can you move to the next slide? Yeah, so what we're going to talk about today is, in previous sessions, we've discussed a lot about the workings of EVPN within a single domain. We've talked about single homing, how to do multi-homing. We've talked about MLAG, all active topologies, different IRB models, and we'll also discuss multicast. What we're going to cover today is really kind of look at solutions and the role of an EVPN gateway for building multi-EVPN domains. In terms of the EVPN gateway, what we're trying to achieve here is kind of two types of problems. The first kind of a solution we're looking to do with our EVPN gateway is the idea of building an EVPN DCI model, whereby we have multiple EVPN domains geographically dispersed in different sites, and they're interconnected via some sort of MPLS backbone. And there's then a requirement to provide potentially either layer 3 connectivity across the MPLS backbone. So provide layer 3 connectivity between different EVPN domains, but provide it across the MPLS backbone. Or could also be a requirement to provide not just layer 3, but also provide layer 2 as well across the EVPN domains. Right. So that's the first kind of use case, and we'll talk about a little bit that, and we'll do a demonstration of that use case for the EVPN gateway. Second one is kind of more top of the mind. It is really the question of EVPN scaling, right? So we're seeing more and more customers whereby their fabrics themselves, the leaf-spine fabrics, are getting ever bigger, where they're looking to use maybe leaves, 100 leaves inside the fabric, 150 leaves inside the fabric. And at the same time, they want to deploy an any server anywhere model, right? So therefore, stretch their VLANs across every single leaf. Potentially provide layer 3 connectivity across every leaf as well, right? So that then has implications in terms of flood lists. If you're stretching your layer 2 VLANs across that amount of leaf nodes, there's then state churn in terms of MAC addresses, MAC IPs, routes, IMET routes, and then if there is any failure or event within the domain as well, the amount of state churn to actually reconverge the domain. So what we'll talk about as well is, we'll talk about how we can actually provide that any server anywhere model, but provide it in a way where we introduce hierarchy into the design to allow you to actually scale better, therefore reduce the flood domains, reduce the amount of routes and state churn that's actually happening within your EVPN domain, right? Doing all that, so scaling better, but still retaining the capability to do layer 2 and layer 3 stretch within that domain. Okay. So Mitch, can you move to the next slide? Sorry, next one, Mitch. Sorry, next one. Yeah, thanks, Mitch. Yeah, so when we talk about DCI and we talk about interconnecting EVPN domains, right? I mean, certainly we could do that today. You would do that today where traditionally you would maybe have your border leaf inside your local EVPN domain. And then if you wanted to stretch across your MPLS backbone, you would do some sort of option A handoff, where you do a VRF-like handoff onto the PE node. The PE node would then be running IPVPN or EVPN MPLS, learn the local routes of the local EVPN domain, and then re-advertise them as IPVPN routes, right? So that's something we could certainly do today. And you could do a similar type of option A VLAN handoff model if you want to actually interconnect two EVPN domains within the same site, right? So certainly that's a solution that's happening, it's possible today. What we're talking about though is with the EVPN gateway is actually giving you the capability to actually collapse that two-box solution. So one box providing the connectivity to the EVPN domain, and another box providing connectivity to the MPLS domain, actually collapsing that functionality into a single box, right? Which we're terming as the EVPN gateway. And with that EVPN gateway, we can now provide connectivity to the local EVPN domain and provide a hierarchical model to also at the same time scope the local routes and what you advertise to any neighboring EVPN domain. And you'll say it could be in the same DC. and also provide MPLS functionality where we can actually do address level translation, where it would be between EVPN and IPVPN, or encapsulation chain, right, in the forwarding plane. So go from EVPN VXLAN within the DC on the same gateway node, actually translate the forwarding plane into MPLS, right? So the whole point when we talk about EVPN gateways is we're talking about the idea of now moving a model where we traditionally would do something in 2 boxes. We're actually going to collapse that into a single box, right, to give you the benefit. And then by doing it in a single box, it means there's less boxes to touch in terms of deployment of the service itself, right? No need to go to the border leaf, do the VRF-like configuration, and also then go and touch the PE node as well, right? In the EVPN gateway, we can do all that within a single node. Move to the next slide, Mitch. So as you can imagine, we're talking here about not just a single solution here, we're talking about multiple solutions. So we're talking about translating different address families. We're talking about going from EVPN to IVPN. We're also talking about translation between different encapsulation modules. We're talking about going from VXLAN to MPLS as well. So there is a number of standards out there which kind of define these different models, right? Whether it be layer 3 and layer 2. So for the layer 3 model, when we talk about translating between EVPN and IPVPN, so a layer 3 model on the gateway, it's a pretty much mature standard. That's the layer 2 VPN EVPN draft we're talking about here. It's kind of something we'll demonstrate, but it's something pretty mature and it's supported across multiple vendors. When we start looking at the separate solutions where we talk about providing layer 2 stretch across EVPN domains or across MPLS, there is actually multiple drafts, right? Multiple drafts in terms of the look to solve a similar problem. They're not a one-for-one mapping. There is the DCI EVPN draft, and the DCI EVPN draft is very far-reaching in terms of the fact that it looks to address multiple encapsulations. So it looks to address the problem for stretching layer 2, not just from a VXLAN perspective, but VXLAN with MPLS. Also looks to address it with provider backbone bridging as well. It looks to also not just look at it as EVPN control plane, but it looks to also solve it when you have VPLS in your backbone, right? The Sharma draft is slightly more restricted, slightly less uptake across the industry, and it really just focuses on one use case, which is just EVPN VXLAN to EVPN VXLAN. Right? So in our demonstrations, in our implementation, we're looking at the wider ranging DCI EVPN draft, and that's what we'll be demonstrating today. We're looking at the Sharma draft because it's pretty restricting in terms of what functionality it'll deliver, right? So when Mitch goes through the different solutions, we'll show you the layer 3 solution, so the IPVPN, and then we'll look at the layer 2 DCI, layer 3 DCI as well with VXLAN. Okay. Move to the next slide. So just to summarize here, what we're going to be showing you here in the sort of graphical, give you a graphical view of it, is we're going to be using this EVPN gateway. And when we talk about the EVPN gateway, it's the same box doing all these functionalities. So what we're talking about is, one, we'll show you how to have an EVPN domain and interconnect 2 separate EVPN domains and interconnect them via MPLS. And between the 2 domains, you're going to have the gateway itself running as a PE, and it'll be running IPVPN. So what that means is it will take the local type 5 routes and then re-advertise those type 5 routes as IPVPN MPLS routes, right? And therefore providing layer 3 connectivity between the 2 domains, right? And then we'll show you as well a slightly different model, which is now same use case where I have 2 EVPN domains. They're interconnected via MPLS. But we can also show you as well how you can actually, when it's implemented MPLS, but I want to stretch layer 2, I can then run, instead of IPVPN, I can now run EVPN MPLS between the 2 gateways. And now I can provide layer 2 and layer 3 between my 2 sites. And then finally, we'll show you also this EVPN gateway functioning whereby I now have IP connectivity between my, not MPLS, but IP between my different domains. And what we'll show you here is how you can then use the EVPN gateway to actually provide some sort of level of hierarchy and therefore allow you to scale your layer 2 domains, therefore reduce your flood lists and the amount of state churn that's going to exist across the different domains. All right, Mitch. So I'm going to hand over to Mitch, and Mitch is then going to go through the demos individually. Over to you, Mitch.
All right, cool. Thank you, Alex. And quick thank you again to everyone out there that has made the time to join the party today. As usual, As you can imagine, after Alex's overview, we have quite a bit of ground to cover. And while we've squeaked just across the finish line in our previous sessions, this may be the one that finally breaks that 1 hour limit. So we'll just get to it. Let's jump in and let's see how we do. So just as in previous sessions, we're going to be going through a series of live demos. And in each demo, we will, of course, do a conceptual overview of the topic, but we'll ultimately end up taking these concepts off of the whiteboard and into the lab. So while in the lab, we will enter our configurations, validate control plane state, and confirm data plane operations via end host connectivity, as well as some packet captures, just to make sure that what we're seeing on the wire is what we actually expect to see. Now, one may look at this list and say, okay, 1, 2, 3, wait a minute. Didn't Alex just cover some use cases that are supported but are not listed here? And if someone is thinking that, they would be correct. So these demos were selected in the interest of time, but other use cases such as MPLS EVPN to VXLAN EVPN are indeed supported. Also, as called out earlier, today's session is the 7th installment in our little series here. So again, to those that have attended or watched the previous sessions, thank you. It's been a lot of fun putting these together so far, and please keep the feedback coming in. Actually, today's topic was the result of feedback that we'd received. So we'll talk more about future sessions towards the end of today's presentation, but again, thanks for joining in. Also, as a reminder, the sessions do build upon each other. So while we're, of course, going to be referencing core route types, MLAG, active-active multi-homing concepts, etc., we won't be spending much or really any time covering the details of these specific topics. But if you feel the need for a refresher or you need an action-packed series to watch, all of these sessions are recorded and available over at events.arista.com/webinars. All right, so before we actually jump into our first demo, let's take a minute and get familiar with the lab that we're going to be spending our time in today. So for those that attended previous sessions, one thing will likely stand out here. The lab has grown a lot, which is good. Who does want more switches? But this does give us the ability to really demonstrate multiple EVPN domains with an interconnect that may be either MPLS or IP transport. So the first thing to note here is that we have two fabrics. We have fabric A and we have fabric B. These two fabrics are connected together via the backbone transit devices, BB1 and BB2 respectively. So the loopback interfaces, as usual, are going to serve important roles today. Loopback 0 is going to serve as a device's globally unique address, while also being leveraged as the source of any overlay peering sessions in BGP, so IPVPN, EVPN. If a node is a member of an MPLS domain, then loopback 0 will also serve as that node's PE address. So loopback 2, on the other hand, it's a pretty simple job today. It's the VTEP address. That's it, right? One and only purpose in today's demos. One thing to call out with these loopback addresses, you see 11XY or 22XY, the third octet in each respective loopback address is going to represent which physical fabric that node is a part of. So if we see, for example, like spine 1 is 111201, and then over here we have B spine 1, which is 112201, or 111201 and 112201. It's important to keep this stuff straight as we'll be going through our examples today. 1 equals fabric A and 2 equals fabric B, right? So we'll always do our best to make sure we reference which particular fabric a node is in when we're looking at the control plane state. But just remember, 1 is physical fabric A and 2 is physical fabric B. So finally, the fourth octet will represent that node's respective device ID. And in the case of MLAG, which we will see in demos 2 and 3, loopback 1 will be the same address on the border leaf nodes in each respective fabric. Those will be serving as our gateway nodes. All right, so we'll come back to this diagram from time to time if needed, just for reference. But with that intro complete, let's get to it. All right, so use case 1 for our first demo, we're gonna cover the EVPN gateway to IPVPN MPLS model. So we have an IP, in this case, we have our MPLS interconnect between the two different fabrics. So in our subset of the topology, we have VXLAN EVPN domain 1 in fabric A, and then we have VXLAN EVPN domain 2 in fabric B. So these two fabrics are in different geographic locations, interconnected via an MPLS backbone and an IPVPN control plane. So Alex called this out earlier. Traditionally, we could use two boxes to solve this problem with like an option A type handoff. But with the EVPN gateway functionality, we can collapse this solution into a single box, into a single gateway node. Now, with that being said, notice in our topology, we do have two gateway nodes in each respective fabric, but this is just for the purpose of redundancy. Both of these gateway nodes are acting as simultaneously as PEs and VTEPs. So in addition to peering EVPN with the spine in their respective fabric, so over here we have fabric A, fabric B, peering in the EVPN address family in their respective VXLAN domain, the border leaf devices are also peering with a centralized IPVPN route reflector. Now, ultimately, the goal of this demo is going to be let's enable IP communication between host C and host F. Now, this communication is currently broken, and we're going to take a look at why. So once we've identified the problem, we'll hop into the configs and provide a solution. All right. So let's actually go ahead and take this off the whiteboard and let's pivot into the lab. All right, so let's go ahead and see first how we're going to test communication between host C and host F. And there is a very extravagant bash script we're going to use. It's just using fping on a list of IPs that is equally as impressive. It's a list of one IP address. And what we're going to do here is just have this run. And right now we see that there's no bueno, not good news. It's not reachable. So all right, we're going to take a look at what's going on here. All right, so first let's take a look on our IPVPN route reflector, which happens to be backbone 1 in this case. Do we have the active IPVPN peering sessions? So VPN, IPv4, summary, up with the border leaf devices at each respective fabric, and we do. All right, so the peerings are up, but as we can see, we're receiving a whole lot of nothing. So let's actually do this. Let's keep this running. Let's do watch 1, show BGP, VPN, IPv4. Let's let that run. So this is going to refresh the output of that command every second. And right now, as expected, there's nothing here, right? We're looking for the VPN v4 routes. Nothing's coming from the border leaf nodes. But then let's go ahead and take a look at the border leaf nodes themselves and see, do they have a route, at least to the destination, in their respective domain? All right, so we'll pick on ABL1A in this case. We'll do show IP route, BRFA. And yep, so as expected, we have a route to the 30 network. And we can tell just by looking at the information in this route, we have a VTEP. So next hop VTEP of 221.101, which is this guy over here. It's using an L3 VNI of 50,001. So this immediately tells us VXLAN. And then we have the EVPN router MAC that is associated with the VTEP originating this control plane state. Okay, all good, but we don't see the 40 network. So if we go over to the other side now, and we do show IP route, BRFA, we see the 40 network, and the gang's all here. We have the VTEP, the L3 VNI, the EVPN router MAC, but there's no 30 network, right? So we see the problem. All right, fabric A doesn't know how to get to 40, and fabric B doesn't know how to get to 30. So in other words, the type 5 route being received by the border leaf nodes for the network in their respective domain is not making it into the IPVPN control plane. Right, so in order to fix this, so right now this is what we've got. That route makes it here, but then it just doesn't go anywhere else. They program a proper forwarding entry, but they don't pass along the information. So in order to fix this, we're going to need to enable the gateway functionality on the border leaf nodes. Now, this will ultimately enable them to originate reachability information for this network, for the network in their respective domain, into the IPVPN control plane. All right, so in this case, we see that type 5 route is being taken, and we have the 30 network originated here. There's the prefix, route distinguisher, VPN label, route target, the usual suspects. right? So we could leverage a single gateway to accomplish this. But again, in our environment here, we have redundancy just to ensure that if a gateway goes down, we don't lose connectivity. Now, this is good from a resiliency standpoint, having two gateways, but it also introduces the potential for a control plane loop, right? So for example, if we have gateway node BL, let's say BL1B sends this route out, and the reflector just sends it right back down here to this client, we need to make sure that when this route is received by this gateway node, it doesn't take it and say, oh, cool, thanks. Let me send this in as a type 5 into the EVPN domain. Because at this point in time, it'll come right back here and the process repeats, right? We'll have a control plane loop. Now, we can, of course, solve this manually. We can leverage the route maps, extended communities, tags, et cetera. There's ways to accomplish this. But thankfully, the EVPN IPVPN interop draft has given us a built-in method of preventing these control plane loops from occurring. So that method is the dpath attribute, right? So here we have the domain path, and this is going to be seen as like a little breadcrumb trail. So we'll see in a second when we enable the gateway functionality in the config, we're going to specify that on these gateway nodes in Fabric A, the domain ID for the EVPN control plane domain 1 is 65100:1. And then we'll set a domain ID for the IPVPN control plane. That'll be 65300:1, if I recall correctly. But the idea is that when we see that domain ID in that breadcrumb trail on the dpath attribute, and if it's a domain that we are a part of, we're going to drop that route. So we have some loop prevention kind of built in here, which is nice. So now look, we're going to go ahead and enable that gateway functionality. But as we saw earlier, the lab has grown a bit. And so now we need to make some configuration changes on all 4 border leaf nodes so that we can complete the picture here, right? So this guy's going to take the IPVPN route and then re-originate it in his own local domain as a type 5 route. All right, but to enable this now, we have a bit more touch points than we had in previous sessions. So in order to save some time, we're actually going to automate this process. So we're going to pivot over here. We're going to look at VS Code. And just as we saw with our extravagant health check bash script, we have equally impressive bash scripts to run just some simple Ansible playbooks. Right, so just to kind of show like nothing up the sleeve here, what's going on, we're just going to run a config push playbook that's going to use the EOS config module to just say, hey, if someone sets the model variable to IPVPN gateway enabled, take this config and replace the config on the device, right? So what we'll do is we'll actually kick this off now, and we'll say IPVPN with gateway. And then what we should see is that this configuration is going to be pushed to the devices. But actually, while that's pushing, let's take a look at what is changing, right? And it's cool that we're automating it, but we still need to understand what are the differences. So again, we'll just sit in VS Code and do a very simple side-by-side diff, and we'll pick on the gateway node A border leaf 1A. So we'll look at no gateway versus gateway, and then we'll come down here and see that, okay, well, first, nothing too crazy here. We're just changing the host name so we know is the gateway enabled or not. But if we get to the meat of it here, like what's actually happening, one of the first things we're doing is under the BGP config, we are adding the BGP best path dpath command. So this is now going to make dpath part of the best path selection process. So if we receive a couple routes and they're equal up to the point where we evaluate dpath attribute, we're going to choose the one that has a shorter dpath and also doesn't include our domain. So if it includes our domain, game over, that route's getting dropped, right? Come down a little further, we're setting the domain identifier for the EVPN domain to 65100:1. And this is in domain 1, Fabric A. We also have under the VPN v4 address family, the domain 65300:1 is defined here. And then last but not least, we're configuring the route targets, right? So before we had just the EVPN route targets under VRFA. Now we have the route targets for the VPN v4 address family, right? So import and export. And one thing I do want to call out here is that these route targets could be the same. In a lot of deployment scenarios, they'd likely be different, right? If maybe this is a new environment and we have an existing IPVPN MPLS domain and we don't want to change RTs, that's fine, right? So the route targets for EVPN can be completely different from the route targets being used for VPN v4. But to kind of summarize here, this will be true in a lot of our examples today. It's a classic case of understanding the protocol, not the config, right? Because as you can see, this took maybe 5 lines of config to really enable this functionality. But really, it's what's happening behind the scenes that's most important, so that we can, understand how to support and troubleshoot it. Right. So if we look at host C now, we can now reach host F. That's great, but let's actually see what happened. Right. So let's go ahead and hop over to the BB1 node. So again, this is our VPN v4 IPVPN route reflector, and it is now receiving the 30 network from the gateway nodes in Fabric A, and it's receiving the 40 network from the gateway nodes in Fabric B. Now, if we hop back over to those gateway nodes, we should see, Fabric A now has the 40 network, and we can see it's reachable via, an MPLS domain. So we have the transport label here and the VPN label here. And then likewise over in Fabric B, we should see show IP route VRFA, and awesome. We have the 30 network, transport label, VPN label. The control plane looks good. And as expected, things are working. But let's make sure that we're actually seeing on the wire what we're expecting to see, right? So let's actually go back to our physical topology here, and let's run some packet captures. So we're going to run some captures here first on A spine 1. And what we should see here for this first capture is that from A leaf 1A to one of the gateway nodes, it could land on either one. This should be VXLAN encapsulated. For the next step, we should see that between the gateway nodes, this will be MPLS. So we should see a transport and a VPN label. Then last but not least, we should see that the final path over to the 40 network over to host F is going to be, again, VXLAN. So it looks cool on a whiteboard. Let's actually see it in action. So let's go ahead and take a look here. And let's say on A spine 1, we'll start a packet capture. And let's look just for ICMP to cut down on some noise. And if we look at this, we see that, yep, so this is host C. The 40 device is host F. And the VNI is 50,001. Actually, let's move this over here for clarity. So the L3 VNI is as expected. This is VXLAN uncapped. And it's coming from, in this case, A leaf 1A. Let's erase some of this ink here. So it's coming from this node here. And it shows border leaf 1B. Yeah, no big deal. That's fine. So it's going over to 222 or 221.106. And then at this point, let's now look at the backbone. So far, so good. Now the backbone, now let's forget about domain 1. We're going to focus right here. And what we should see, again, if we just look for ICMP to cut down on some of the noise, we should see, yep, there we go. We see that this is now MPLS. So it's still host C to host F, but now here's the transport label, and here's the bottom of the stack. Here is the VPN label, so that the receiving PE can do the lookup and forwarding operation in the proper VRF. All right, so far so good. Let's see if we can bring this home with the main event. B spine 1, we should see that this is again VXLAN. So let's again ICMP, cut down on that noise. Yep, there's host C, host F, VXLAN uncapped, L3 VNI, and there are the VTEP IPs. All right, so far so good. That is actually, the data plane is validated, and with that actually kind of wraps up use case 1. And while we're gonna go ahead and pause and set the stage for the next use case, which is going to transition us to a IP interconnect between the two domains. But while we're doing that, Alex, Russ, any questions you guys want to touch on?
Yeah, I've got a couple of quick questions that come in. So I'll give them to you, Russ. So the first one, in the setup you had, Mitch, you had 2 gateways, I believe, in each of the sites. So I think the question here, Russ, is it limited to 2 gateways? Can you have more than 2 if we want further redundancy or resiliency?
Right, yeah. So for the layer 3 gateway that we're looking at now, and it's not restricted, you can have, as many gateways, pure layer 3 as you need. So it can be scaled out in this case.
Okay, and I'd probably follow on for that, which was a question really around the DPath, right? How does that DPath work on the gateway itself? I think the question really was, where do you configure the DPath on the shared gateways, and how is it shared in the MPLS domain as well?
Yeah, and I think Mitch touched on it. So where it's configured, you configure it under the BGP sort of strata, as well as enabling the DPath to be part of the best path selection process. But the DPaths themselves, you use the same DPath values in each site. So for VXLAN would be 1 for all gateways on that site, then MPLS would be another for all PEs in that site. The other site, of course, would have other values. And then with regards to how it works, I know Mitch touched on it, but just to reiterate, the DPath that chooses the shortest DPath value. So in that instance, and that's actually enabled by that best path configuration option that you saw, where you're enabling DPath. But the loop prevention itself is always active when you have DPath values configured. So it's a very easy button way of stopping mutual redistribution when you have multiple gateways.
Probably final one was really like, what's the typical use case for this, given the fact that it's only layer 3?
Yeah, the typical use case for the IPVPN one is, again, really if you have existing IPVPN deployments out there and you need to interact with brownfield, as we call it. So that's the primary use case really, which customers are looking at for this case. But if you wanted to extend that from not just for layer 3 and or layer 2, there's the option of EVPN MPLS in that sort of core domain, as it were. And there you have the option to potentially start with layer 3 and then extend to layer 2, as the case may be. So the real driver for the layer 3 case is brownfield ready, where you have existing IPVPN deployments.
All right. Thanks, Ross, for that.
And sure. And I would say we're getting a number of questions coming in. So all this has been done live, so it's great to go through, and we'll answer as many as we can as well. So keep asking questions.
Yeah,
as many as you can. We have a few people here.
Yeah, so worth pointing out, if you do have a question, please put it in the Q&A window, and we'll try to answer on live. Back to you, Mitch.
All right, cool. Yeah, I kind of forgot to mention that. This is live. Anything can happen. So cool. Good stuff, guys. Thank you. So we're going to jump into use case 2A, and here we're going to shift our focus. Right, so here we are now going to look at the EVPN gateway we have a EVPN VXLAN interconnect, essentially an IP interconnect between the two physical fabrics. And again, sure, our lab has grown since the last session, but it's certainly still nowhere near the size of a large production deployment where we could have hundreds of VTEPs, where we'd like to see or have the ability to connect any workload to any VTEP anywhere. And a deployment of that size could see thousands of VLANs, stretched across all the VTEPs and all the fun that comes with it, right? You could result in large flood lists, large MAC address tables, and all the control plane state and potential churn that comes with that. So in order to better scale, the EVPN gateway functionality is going to introduce a level of hierarchy and scope, giving us the ability to scale our EVPN deployment while still retaining all of the functionality we had in a single EVPN domain. In other words, we can still connect any workload to any VTEP and maintain that layer 2 and 3 connectivity. So demo 2 is going to be split into 3 phases. And this is really going to be to illustrate the impact the EVPN gateway has on the scope of the control plane and ultimately the behavior of the data plane. So we are going to pivot between a single EVPN domain, in other words, no gateway, and multiple EVPN domains, in other words, adding the gateway, as we discuss each of the following route types. All right, so we have type 1 and 4 for active-active multi-homing, type 3 routes, specifically how they pertain to the flood list and the flooding behavior. We'll touch on some of the rule sets when it comes to the gateway node flooding. And then also, finally, we'll look at the type 2 routes and the bridging behaviors. Now, the first time we make the pivot from that single domain to multiple domains, we will review the configuration changes that were needed to enable the EVPN gateway functionality on the border leaves together. So we'll pause and we'll take a look and say, okay, before we keep going, what configuration changes were actually needed? We won't review that configuration anymore when we pivot in the future because they're going to be exactly the same. All right, so before we jump in here, let's take a look at, and to start making changes, let's look at what the control plane peering differences are going to be between each of our models. All right, so in the single EVPN domain configuration, again, no gateway, each VTEP will peer with the spine in its own respective physical fabric, right? So fabric A peers with A spine 1, fabric B peers with the B spine 1. Now the spines, so the spine in fabric A is going to peer EVPN with the spine in fabric B. Now, ultimately, this is going to result in any EVPN control plane state that originated in fabric A being sent over to fabric B with the attributes such as next hop, route distinguisher, route target, EVPN router MAC, etc., all unchanged. Now, the consequence of this, kind of in addition to the additional control plane state, is like the large flood lists and potential route churn, which we'll talk about in a second here. And also, it means that end-to-end IP reachability must exist between all VTEPs across all of the physical fabrics. Now, in the multiple EVPN domain model, so with this configuration, we've enabled the gateway functionality, right? So we've said, hey, border leaf nodes, you're now gateways. Cool, rock on. Now, with this model, each VTEP still peers EVPN with the spine in its respective domain. However, notice that the spines no longer peer with each other. So instead, we're leveraging a centralized route server for the border leaf nodes to peer with in the EVPN address family. Now, we could have just done a full mesh of peerings directly between the border leaf nodes, and that would have been fine. But to better enable the addition of domains in the future, maybe the next domain 3, 4, 5, whatever, we've opted to use a centralized route server to ease that onboarding in the future. And also, for the demos in this use case, notice that loopback 1 on the border leaf nodes in each respective fabric is identical. All right, so in fabric B, 222.199 is the VTEP address. In fabric A, 221.199 is the VTEP address. And that's because these gateway nodes are running in an MLAG deployment. So we have redundancy from a gateway node standpoint just through the use of MLAG in this particular model. All right, so let's actually, again, let's take this off the diagram and let's just jump in and let's cover type 1 and type 4 routes. All right, so if we go here and look at the behavioral differences, the first one we're going to look at here is the type 4 route or the type 1 route. So a type 1 route, in this case, we have a single domain and we have A-leaf-1A and A-leaf-1B, they're dual home to, in this case, host C. Right, just for the sake of clarity, we're only going to show the control plane from the perspective of A-leaf-1A, but he is going to originate a type 1 per Ethernet segment route for this multi-home segment. This route is going to be sent into the control plane and ultimately received by every VTEP across all domains. All right, so there's the per Ethernet segment and the per EVI variants of the type 1 route. Now, it's additional control plane state, sure, but it also can introduce unnecessary churn if, for example, A-leaf-1A loses his connectivity to the ESI, the segment of C. It's going to withdraw this per Ethernet segment route, which is also referred to as a mass withdrawal route, to signal to the rest of the environment that, hey, if you have me as a valid next hop for any MAC addresses on ESIC, please go ahead and remove me as a valid next hop for those MAC addresses. So all of these VTEPs over here receive that, and then they update their forwarding plane accordingly. You know, likewise with the MAC aliasing routes, and then also all of the type 2 routes that are then withdrawn after the fact, right? So this can introduce some unnecessary churn if an ESI connection is lost, comes back up, etc. So let's actually take a look at this control plane state and confirm that that's actually what we're seeing, right? So if we look at this, we'll do a show BGP EVPN route type auto discovery, so type 1 routes. And let's take a look here. So right now, this CLI session is right over here on B-leaf-1B. All right, so we're taking a look at this and we see that it has the ESI for C. Now there's a couple other ESIs present on A leaf 1A, and there's host A and host G. So all of those type 1s are making it over to B leaf 1B. All right, so let's go ahead and enable the gateway functionality, and let's see what happens to these routes. And actually, though, before we do that, let's go ahead and see, let's look at the type 2 routes as well. Or I'm sorry, the type 4 routes as well. All right, so these are not quite as, actually, they're not nearly as impactful as like the type 1 routes, because these are just hanging out in the rib, but the VTEP isn't really taking any action. They're just additional state. Right, the type 1 routes are really the focus here because these will cause local forwarding plane decisions on the VTEP based upon the information in these routes. But in short, we should see both of these go away when we enable the gateway functionality, right? Which is ultimately going to end up performing, doing this, where it's, all right, we have this type 1 route, it stays within our local domain, and the gateways say, nope, you're not leaving, right? So the type 1 routes stay local. So before we make this change, actually, let's go ahead and here's our list of IPs. We're going to run a ping from host A, which exists over here on A leaf 1A. And there's a multitude of other hosts that exist all over the environment, and we're going to ping all of them. All right, so again, our fancy bash script, and cool, looks good. Everyone's alive. So all good. Let's go ahead and make this change. Let's enable the gateway functionality and keep an eye on what happens to the type 1 routes and the type 4 routes in Fabric B. All right, so let's come here and let's say, you know what? We are going to enable gateway functionality. And let's go ahead and close this out. And hoping, oh, we didn't catch it in time, but they're gone. Spoiler alert, the routes disappear. So the type 1 routes are now gone from Fabric B. The type 4 routes that originated in Fabric A are also gone from Fabric B. So remote fabric type 1 and type 4 routes are gone. But everything's still up and running. All right, so everything's good, right? If we look at, like, for example, how the heck do we reach some of these MAC addresses or whatever, we're going to look at this a bit more when we get into the type 2s and the type 5s. But the point here is that we just kind of showed that we don't really need those routes in these remote fabrics to maintain reachability, both from a bridging and routing standpoint between our end hosts. So the next question is kind of, okay, what just happened, right? Okay, what configuration, what does this look like? So let's pause and let's actually review exactly that, what happened. So we're going to compare again. We'll keep picking on ABL1A. And again, we see that, okay, the host name changed, just so we know we're no gateway or we are a gateway. But let's get down to the meat of the config. So we added a peer group called EVPN remote peers. Okay, this is nothing in this is gateway specific, right? It's remote AS, update source, etc. Okay. Next, we added a route server into that peer group, EVPN remote peers. Okay, par for the course, still nothing gateway specific. Next, we then went into the EVPN address family, and we activated the peers that are a part of the remote peers peer group. Okay, again, nothing gateway specific. Aha. If there was something that could be seen as the on-off switch for the gateway functionality, this is the command. What we're doing here is we're telling the device that, hey, if you establish a peering with a neighbor in the EVPN address family, and they are a part of the EVPN remote peers peer group, flag that peer as a remote domain peer. This is important because this is then going to influence not only flooding, as we'll see in a minute when we cover type 3s, but also what route distinguishers and what route targets do we use. So notice before we had route distinguisher for local domain, and we still have route distinguisher for local domain in our new config. But we've added the route distinguisher that is going to be used when originating control plane state, or these EVPN routes, to that central route server. So we're going to use a different route distinguisher in this case, just so we can easily tell, okay, is this an inter-domain route? Now, these could be the same, that would be totally fine. But just for clarity's sake, we wanted to make them different here. And the same holds true for the route targets. The route targets could be different. So we could use these route targets for our local domain route origination, or And we could use a different route target for origination of routes to the remote domain peers. In this case, we just kept them the same just for simplicity's sake, but just know that these can be different. So again, and we'll talk more about this command here once we get down to demo 3, where we're going to cover type 5 routes and specifically L3 gateway. But again, looking at this right now, there's not a ton of configuration here, right? This goes back to that whole know the protocol, not the config methodology, where it's all right, well, we put the config in, but then, what happens? So as we saw, the type 1 and type 4 routes are gone, but we still have reachability. Okay, very good. Let's take a look next at what happens to type 3 routes. So now we're getting into the discussion around flooding, flood domains, local, remote, etc. Right, so, and actually, you know what, in order to best illustrate this, let's go back. Let's disable the gateway functionality so we can really show this behavior. So no gateway, we'll push those configs, replace them, and then we should see here that those type 1 routes are going to come back because we're going to be in a single EVPN domain. And then we should also see eventually that there they are. We should see the type 4s are back too. All right, cool. There they are. They've made their return. So at this point, we are now back in a single domain configuration. So let's actually make the diagram a bit larger here and take a look at, from a type 3 route standpoint, what are the implications of having what's the result of having a single domain? All right, so ALEAF1A in this case is originating a type 3 route. And it's got the usual suspects, right? Here is the VTEP IP. So here's the route target for that MAC VRF. Here's the L2 VNI, et cetera, et cetera. All that is just a fancy way of saying, hey, if you have a broadcast frame in VLAN 10, please send it to me. That's ultimately what this thing is saying. And when that route goes out to the control plane, every single VTEP, again, in a single domain, is going to receive that type 3 route unmodified. So everything in Fabric A, as expected, is going to receive the route, and we'll focus on ALEAF2A. It's going to add the VTEP 221.101 to its flood list for VLAN 10. Cool, all good. But over in Fabric B, the same holds true. So in this case, we'll pick on BLEAF1B again. He's been a good sport. So on BLEAF1B, he receives the route and says, okay, cool. For my VLAN 10 flood list, I better add 2.2.1.101. Now, this means, of course, end-to-end IP reachability must exist between the VTEPs, but this also means, in our lab, this isn't a very large topology, but if we had hundreds of VTEPs across a single domain, you can imagine that the flood list could get pretty large. All right, so let's actually look at this in the lab and see what does our flood list currently look like. So let's go ahead and go here and say watch one show VXLAN flood VTEP. All right. So right now, this command is running on BLEAF2A. So this guy right here. And he's seeing that in his flood list, if he receives a broadcast frame in VLAN 10, we need to make sure we send a copy to all of these VTEPs. And we can see right here that this is Fabric A, Fabric A, Fabric A, Fabric A. There's only 3 of them. Of the 7, there are only 3 in the flood list that are actually in the local domain. Right, so let's go ahead and go back and enable the gateway functionality and see what happens to the flood list. And then we'll kind of talk through what changed with the control plane. All right, so let's go back here, our trusty VS Code, and let's re-enable that gateway functionality. So we're going to push the config on the right back to the gateway nodes. And I should call out that while this configuration is pushing, this configuration, except for the route distinguisher, is going to be identical across all of the gateway nodes. Right, so this isn't super specific to ABL1A, except for the route distinguisher value, where we want that to be unique. Everything else can be the same. All right, so missed it again. Spoiler alert, it shrinks. So the flood list, in this case, now on BLEAF2A, it only has entries in its flood list for VLAN 10 for VTEPs that exist in its own respective domain. All right, so how the heck do these broadcast packets actually make it over to Fabric A? And also, how did the control plane change? What just happened here? So if we go to this diagram and take a look at this, we see that in this case, with the gateway functionality enabled, the type 3 route originated from ALEAF1A, as expected, and also as expected, the VTEPs added that VTEP to their local flood list for VLAN 10. Actually, local is a very key word here. So on the gateway, it's going to add VLAN 10 to its local flood list. More on this in a second, but the gateways are now going to maintain two separate flood lists, a local and a remote flood list. So next, the gateway nodes are going to advertise their own type 3 route to their interdomain peer. So in this case, we're sending it up to the route server. Again, it's a type 3. Notice that the route distinguisher is our interdomain value here, so 331. And the VTEP IP is just that shared VTEP IP between the MLAG'd gateway nodes. And aside from that, everything else is the same, right? We have the usual MAC VRF route target. We have the L2 VNI, all good. So over here now in Fabric B, the gateway nodes receive that route. And they look at it and they go, oh, cool. I'm going to go ahead and add 221.199, all right, so that remote gateway shared VTEP IP, to my remote flood list for VLAN 10. So more on that in a second, but ultimately, they were either already or they will now originate a type 3 route into the EVPN control plane in domain 2, which will lead to the VTEPs in that domain populating their flood list with the appropriate information, right? So they're going to say, hey, if I have a broadcast frame in VLAN 10, I need to make sure that this VTEP gets a copy of that, which is the gateway node shared VTEP IP in their local domain. Phew. All right. So what does this mean from a data plane standpoint? What this means is that now if a broadcast frame is received in on B leaf 1B, it is going to send a copy of that broadcast frame, VX line uncapped, to each VTEP within its respective domain. Cool, as expected, all good. It is not going to send a copy unicasted to VTEPs in any other remote domain. What's going to happen now is the gateway is going to receive that broadcast packet. It's going to decap it. It's going to take a look and say, oh, well, this is a broadcast packet. I'm going to flood it out my front panel interfaces, including across the MLAG peer link. Now, as an important note here, the gateway node that received the broadcast frame via the MLAG peer link, so BL1A in this case, it will look at that and it'll say, okay, I received this broadcast frame across the MLAG peer link. I'm going to flood this out my front panel interfaces because there could be locally attached hosts here, like single homed hosts, that need to get this broadcast frame. So we'll flood it out the front panel interfaces, but what will not happen is this will not take that broadcast frame and go, hey, let me send it right back out to everyone, either remote or local. That does not happen. So up here, nope, it's not going anywhere. All right, so this is just a loop prevention check that enables us to have single homed hosts connected on MLAG gateway nodes. All right, so next, the gateway node BL1B is going to take that broadcast frame that it received and it's going to say, okay, I need to make sure that my remote domain peers get a copy of this broadcast frame in VLAN 10, because they send a type 3 route for that EVI. So unicast a copy over to here and the process repeats, right? Flood local, across peer link, flood local, do not send out VXLAN on the other gateway node, and then unicast to all VTEPs in that gateway's respective domain. All right, so this maintains a smaller flood list, and it also, again, IP reachability isn't really required between VTEPs in the different remote domains at this point. But it does bring up that concept of local versus remote flood lists. So over in Fabric A, those gateway nodes, they see their local domain VTEPs as local, and they see the remote domain VTEPs as, surprise, remote. But how do they make this determination? This determination is made because the type 3 route that said, hey, I want broadcast traffic for VLAN 10, which came from 222.199, that came from an interdomain peer, so one of those domain remote peers. So when we receive that, it says, aha, you are a remote domain peer. I'm going to add you to my flood list, but it's going to be for the remote domain, not local. And then vice versa over in Fabric B. This is important because it actually feeds a set of rules here, right? So we have the locally connected host sending in a broadcast, and then it floods out here to other locally connected hosts, local domain VTEPs, and remote domain VTEPs. Okay. But what if it comes in from a local domain VTEP? Then there's a check to say, okay, I should not flood this out to other local domain VTEPs. At best, it's a duplicate broadcast. At worst, it's a loop. So we don't do that. But it will go to remote domain gateways, and it will flood out to locally connected hosts. And then finally, if a broadcast packet is received on the gateway node from a remote domain VTEP, then it will not ricochet that back out to other remote domain gateways. They've already got a copy, right? At best, duplicate, at worst, loop. So we don't want to do that. But it will flood to local domain VTEPs and out to locally connected hosts. All right. I do want to pause really quick before we jump into the type 2 routes here for any questions. So Alex, Russ, anything outstanding right now? Or are we good to keep rolling?
I think we're good to keep rolling. Just, good feedback here. For people, we'll get to the end of this scenario and maybe we'll cover a few aggregate questions.
Okay, that sounds good. Yep, as expected, we're not making that time limit today, but hey, we're having fun. Okay, so next up are the type 2 routes. So before we actually jump in here, let's go ahead and disable the gateway functionality on our border leaves. And then what we're going to do here is, so we should see the flood list kind of increase again from 3 to 7 once we go back to a single domain. So just for fun, we'll watch that. There it is. Womp womp. So it's big flood list again. And then now, if we go here, let's set the stage for watching these, how the type 2 routes are going to actually feed the forwarding plane. So let's do watch one show VXLAN address table. Aha, there we go. And we'll keep picking on host A. Why not? So this is the MAC address of host A. If anyone wants to reach host A, so if you're in Fabric B and you're connected to bleaf1A, it's going to send hey, this is reachable via 221.101 or 221.102. Again, host A is actually dual homed to these nodes. So via the type 1 routes and MAC aliasing, there is actually L2 ECMP to this MAC address. Great, okay. But let's enable the gateway functionality and let's see what happens, right? So let's actually go back here and say, well, let's turn the gateways back on and see what changes, right? This whole time we should maintain reachability, which we are, that's good. But we should see, all right, cool. So control plane convergence, we're good to go, right? So we have now to reach this remote MAC address, we're going to the shared VTEP IP of our local gateway, right? So we will walk through this control plane example, but it's very similar to much of other things that we've seen so far today, right? So we go back to the diagram, make it bigger for some context here. But the type 2 route for host A was originated by bleaf1A. It goes within the local domain. Those local domain VTEPs program their forwarding plane accordingly with the relevant information. Then when we enable the gateway functionality, that type 2 route is going to be originated into the control plane. And there's actually one thing I do want to call out here that's pretty important. There's a pretty fine degree of control around which VLANs we actually want to have type 2 routes propagate outside of our domain for. Right, so in other words, the gateway node, until we actually have the VLAN locally defined, the MAC VRF locally instantiated, and the remote RD and RT values configured, this route isn't going out there, right? If once those 3 things are true, then we'll go ahead and send type 2 routes for that particular EVI out into the interdomain control plane, which is exactly what we're doing here. So the gateway nodes are saying, hey, again, here's the interdomain route distinguisher. Here is the route target for that MAC VRF, the next hop VTEP IP, and the L2 VNI, right? The gang's all here. Over in Fabric B, we see those gateway nodes, they receive these routes and they say, oh, okay, cool. To reach this MAC address, I just need to send it to my remote gateway peer, 221.199, which again is the shared MLAG VTEP IP of Fabric A gateway nodes. And then, of course, the L2 VNI is in there as well. So finally, these guys will re-originate that route as a type 2 into their local domain, which will then result in the VTEPs in domain 2 saying, hey, to reach this MAC address, I need to just go through VTEP 222.199, which is exactly what we saw over here on bleaf 2a. Right, so this goes back to that hierarchy and scope. The gateway is acting as a bit of a demarcation point between different domains. Okay, so that actually wraps up the scenario where we're kind of covering the type 2s. We have one more scenario, and it's use case 2b to go through here. And this is going to focus on the EVPN gateway with VXLAN interconnect. So far, we've looked at L2, right? Bridging, flooding, the type 1s, type 4s, but we haven't looked at the type 5s. So Alex, Russ, any outstanding questions or comments before we jump into this one?
Yeah. I think we'll briefly covered over. I'll just sort of collate some general questions. We've had a lot around, so I'll throw these out to Alex. So for single home devices on the gateway, such as servers or routers, is that supported in this scenario, 2A?
Yeah, so the 2A, we're using the MLAG, which allows us to either, we can have hosts dual homed, obviously, to the nodes in MLAG, but we can also have hosts, if required, singly home to each of the nodes, right? In that case, we don't use the shared VTAP for the next hop. We would then use the local nodes IP for the next hop of any EVPN route. So yes, we can single home or dual home anything to the gateway.
And I mean, we're answering a lot of these route type questions, and so there are a lot of routes being mentioned here. So, you know, I would reiterate, go back and also have a look at earlier ones for different route types. But in general, this solution or DC gateway scaling, are there any new route types here?
No, this is all just built on the same route types as we knew we would use within a single EVPN domain. So no new route types. There's no introduction of any new extended communities either, right? So.
Yeah, and I guess sort of related to the first one, if they're using all active within DCs or using, say, IBGP and EVGP in other places, is there any restriction with the topology in that sense?
So I presume what you mean there is like, do I need to run an IBGP within my domain, or can I run EVGP? Yeah. So with this model, you can run as you're doing today. So if you're running IBGP within your local EVPN, you can carry on with that. If you're running EVGP in your local EVPN, you can carry on with that as well, right? So no restriction in terms of what the BGP topology is to do the gateway.
Okay, I think we'll keep answering the rest online because they keep flooding in, and we'll let Mitch go to get through.
All right,
good
cool.
job, Mitch. Keep going.
All right, thanks. All right, we'll get this. We'll go across the finish line here. So the next thing we'll talk about, and let's actually bring our screens back up here. Let's minimize VS Code. Actually, let's keep this up. So the last piece of configuration that we haven't touched on here is this guy, right? So this one line is saying, hey, as those IP prefix, those type 5 routes are received in the EVPN at control plane, let's take those, we can re-advertise them, set the next hop to ourselves, and send them to our remote domain peers. If I could highlight that, there we go, to our remote domain peers. Right, so let's actually go ahead and see this in action. So if we look at, for example, on ABL1A, I'll show IP route, VRFA. Right, now we're back in the gateway mode of functionality. We see that to reach the 40 network, instead of actually having an entry like we would see here on the right-hand side, where we would say, hey, to get there, we need to go to, either 222.102 or 222.101. Notice that the route has actually been re-originated by the gateway node in Fabric B. Right, so we'll walk through the control plane on this as far as what happened. Right, so instead of a single domain where the route goes everywhere and everyone again needs reachability to this VTAP, the router MAC is the EVPN router MAC is going to be the router MAC associated with a leaf 1A. What's different here? So let's actually make the diagram a bit larger. It's a bit easier to see. All right, so the type 5 route is originated by a leaf 1A. It's a 30 network, L3 VNI, the IPVRF route target. Again, the usual suspects, right? So it's all here. The VTAPs in Fabric A take the information and then program their forwarding entries accordingly. Okay, cool. In order to reach this prefix, I'm going to use this next hop VTAP. I'm going to put this EVPN router MAC in the destination of the inner Ethernet header, and I'm going to use the L3 VNI in the VXLAN header. Cool, all good. The gateway nodes do that same thing, but once we have that gateway functionality enabled, that one line we just looked at, they will then re-advertise this information. So again, we have the prefix. The next hop is modified, as is the EVPN router MAC. All right, so in other words, if you want to get to that route, you don't need reachability. So as a remote domain VTEP, reachability to the loopback of ALEAF1A is no longer required. Because what's going to happen is the gateway nodes in Fabric B are going to then take that received route and then send it into their own local EVPN control plane as their own Type 5. Where again, they say, okay, well, now we're the next hop and you're going to use our EVPN router MAC, but still, import it into the proper VRF and use this L3 VNI in the header, the VXLAN header, when sending this information out. Right, so as you can see over here, on these guys to get to the 30 network, they're just saying send it to 222.199, whereas previously they would have said 221.101 or whoever originated it, right, ALEAF1A. Right, so pretty consistent with the other things that we had seen today, and we just kind of validated that really quick by looking at the control plane. We have the gateway functionality enabled already. So we kind of see that on the A side, to reach the 40 network, we're going to go to our local gateway. And on our local gateway, over on the remote gateway, show IP route VRFA. So gateway is enabled. To reach the 30 network, we're going to go to the remote gateway over in Fabric A. Right, so that's the perspective from the gateway nodes. Let's run the same command on BLEAF1A. Over here, let's kill that command. We show IP route VRFA. And as expected, check out the next hop. The next hop is 222.199, which is, of course, the shared VTEP IP for the gateway nodes in domain 2, Fabric B. And the router MAC is now, it ends in 261009, which is the EVPN router MAC that was sent in the Type 5 route by the gateway nodes in Fabric B. All right, so all good. Gateway functionality enabled, mission accomplished. All right, so with that, we've actually come to the conclusion of all of our use cases that we, it's 2:10, right across the finish line, that we had time for today. So Alex, over to you to wrap it up with the summary, sir.
I think I'm going to pass that one on over to Russ, since I stole you earlier on. So Russ, you want to?
You are, okay. Yeah, so I think as a summary of what we've covered, so I mean, it's a fantastic job, Max, going through all these use cases. You can see the topologies, even much as we cut it down, it's quite a lot. But in general, the resilient gateway solution. So the first one, we termed it here, brownfield DCI. Layer 3 across an existing IPVPN interconnect. It's pretty common. A lot of customers run just standard VPN v4, L3 VPNs. Then there's what we'll term the greenfield DCI, where you have both layer 2 and layer 3 with MPLS, EVPN MPLS interconnect, right? So for layer 2, EVPN VXLAN, layer 3 EVPN MPLS options. And the final one we want to make, I just sort of want to reiterate here is we see often this is termed as DCI, but we're very much viewing this as a scaling solution, building a hierarchy of EVPN gateways for even large data centers. So not necessarily spanning across regions. I think it's very important to understand, right? So this is scaling EVPN domains. We see this is one of the sort of bigger, more important pain points for customers in many cases. Secondly, standards-based, we've called out these standards a couple of times here, but the first one, EVPN, IPVPN for the IPVPN interconnect, and that's with the DPath value, etc. And then for the layer 2, layer 3 one, we're focusing on with regards to what's being tested out there is the DCI EVPN overlay draft. And just a couple of, I guess the final important point, because we've had a lot of questions around 2 bolts, 1 bolts, but so this is the integrated solution, but it's also the same platform doing all of these, all of these gateway options. And I believe I answered a question in the answers or in the question Q&A over there. I think with regards to, a couple of other sort of questions, is this, we show 2 domains. I mean, is this limited to 2 domains? I mean, obviously, Alex might kick that one off, I guess. Obviously, no, I think is the answer there. And finally, like the final sort of question, I guess, is, showing this is, Mitch really showed it in 2B. I mean, you can just use this as a layer 3 solution for the EVPN VXLAN to VXLAN, because there are a lot of customers who use EVPN VXLAN and just IP transport in their quote unquote WAN and they want a gateway scenario where they just, have for L3 and potentially add L2 later on. I mean, with that, did I leave anything out, Alex? Anything you want to add? It's a fun note.
No, I think you're good. Sorry, I was answering your other questions. No, I think you've covered everything. Summarize, yeah.
Okay. And, again, thanks, Mitch. He did an amazing job covering a pretty complex, set of topics to show live. I mean, congrats. It's great work. But, we're always willing for more pain, I guess, or pleasure. So session 8, let us know what you want to see, going forward, because we do have, obviously we've covered EVPN multicast before, but we can sort of add to that. But anything you suggest, we're really using all of the previous webinars, a lot of them in this one alone. So let us know what you want to see.
And just sorry, before we do cut off, Russ, probably what a few questions have been asked. Can we share the configs and such? Like, yes, we can do that. If you reach out to your local SE, we can send them off onto you, or we can maybe post them on EOS Central for the configs and the diagrams. I think that's it.
Cool. All right, everyone. Thanks for joining. Stay safe. And yeah, we'll see you next time.
All right. Thanks, everyone.